EU is online. Hello, testing 1, 2. Okay, good afternoon to everyone. So today is our last lecture. Hopefully we can finish all the syllabus by today and then discuss a little bit on the assignment. I already hand back your assignment. Yeah, you should have received it. I posted out the solution. Maybe we can go through a little bit on the assignment and then go through summary for content after the finals. Okay. I also posted out the quiz for the other class. You also can use that quiz to practice to do some tutorial question, and I also posted out the solution as well. Okay. Um, any question from the last lecture or not? Still busy on your other project or assignments? Haven't started revision yet? Just started. Okay. Yeah. It's not too late to start, okay? Okay, so today we will talk about Stokes theorem and divergence theorem. Okay, so the above equation is the Stokes theorem. Below one is the Green's theorem. Okay, why is it stronger? Because we can derive Green's theorem from Stokes theorem. Okay, yeah. So let's see what's Stokes theorem. So before doing that, let's do one exercise. Okay, let's do one exercise to recall what is the surface integral. Okay, what is surface integral? What is surface integral? Surface integral is a higher dimensional version of line integral. Okay, for line integral, what do you need? For line integral, okay, let me write something down. Say at the front and say at the front. Say at the front. Okay. So let's recall a bit. So what do you need for line integral? Okay. So if you want to integrate a line integral, what do? You need to first parameterize your curve. Okay, give a parameterization of your curve. So you will need to write your C, okay, in terms of some function t. Okay. And this t should have a starting and ending point. Let's call it A and B. Right. Then we can replace the integral to be integration from A to B, okay, of f applied to RT dt. Okay. What else do you need? You need a Jacobian. Okay, the Jacobian in one variable is just the tangent vector. Okay, in one variable is just the tangent vector. Okay. Similarly, for higher uh higher dimensional integration, for example, we want a surface. Okay, let's call our surface x. Okay, our surface x. So we need to, how many variables do we need to parameterize our surface? Surface is how many dimension? Two. Okay, so you need two variables. Then let's call it RUV. And this UV should live on some domain. Let us call D. Okay, UV live in D. Okay. So if I do the surface integral on dx, okay, what is it? It is just integrating on D, okay, of f applied to RUV, okay, and then let's call it dA, okay, we don't put the du dvr. And then what's the Jacobian here? What's the Jacobian when you do surface integral? What's the Jacobian here? Area of parallelogram. What's the area of a parallelogram? Cross product of two vectors. Okay, length of the cross product of two vectors. So what are the two vectors you need to take here? Huh? What's the two vectors you need? Hmm? What's the two vectors you need? Right? Partial derivative with respect to u and v. Okay, so you take the length, okay, of ru cross rv. Okay, so this is the surface integral for a function. Okay, so these are for scalar field. Okay, of scalar field. What I'm talking about is of scalar field. Later we will introduce surface integral for vector field. Okay. Okay, so next, let's do one example here. Okay, let's do one example here. So integrate this z, okay, dx, where x is a surface given by this x1, x2, and x3. Okay, x1, x2, x3. x1 is the side of a cylinder. Okay, you got a cylinder. And then x2 is a disk. Okay, the disk at z equals 0. And x3 is a slender plane. Okay, z equals to 1 plus x. So you got this three object made out by three surface here. Okay, so since these three surface intersect at the boundary, okay, so we can break the surface integral into three parts. Okay, break this into three parts: x1, x2, and x3, because our surface made up by x1, x2, and x3. So if we want to break this integral up, so individually, what should we do? How to compute a surface integral? Hmm? How to compute a surface integral? What's the first thing you need to do? Parameterize your surface. Okay, because you need to get your variable out and then do variation, do integration. Okay, so you need to parameterize your surface. So S1, okay, what is S1 here? Okay, S1 is a cylinder. Okay, S1 is a cylinder. Okay, S1 is a cylinder. So how to parameterize your cylinder? How to parameterize your cylinder? You want to remember? Cylinder is made up by what? Infinitely many circle. Okay, so how do you build a circle here? Hmm? S is cos theta, Y is sin theta. Okay, so what's the radius of my cylinder here? 1. Okay, so there's 1 times cos theta, 1 times sin theta. What's Z? Z is just Z. Okay, but in this case here, is this a proper cylinder or not? Okay, no, right? So how does this Z being controlled? Bounded below by what? The height is bounded below by 0. How about this height here? Bounded above by 1 plus x. Okay, so the Z is from 0 until 1 plus x. So in the theta and Z variable, how do you express this? Where do you take theta from? Okay, you take from 0 to 2 pi because you want the full circle, and the height is going from 0 to 1 plus x. So 1 plus x in here is what? 1 plus cosine theta. Okay, so here is 1 plus cosine theta. Okay, okay, 1 plus cosine theta. Okay, yeah, so let's compute the first one. Okay, so let's compute the first surface integral here. Okay, so what do you need for surface integral here? So I integrate over d. Yeah, I integrate over d. What's my z on my surface here? It is still z. Okay, following the parameterization here, I'm still z. Okay, and then I go to d. Okay. And what's the Jacobian here? Is the length of the first partial derivative with respect to theta cross product with first partial derivative with respect to z. Okay, 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 yeah, okay. So we need to compute this cross product here. So what's this cross product? So sometimes we'll call this a normal vector, right? This is a normal vector to the tangent plane. A normal vector to the tangent. Okay, so what is this? So our differential with respect to theta is minus sine theta, okay, cos theta, 0. Okay. Differential with respect to z is 0, 0, and 1. Okay. So what's this cross product here? Cross product. Cos theta, sine theta, and 0. Okay. And then you need to compute the length of this normal vector. What's the length of this? Or what's the area of the parallelogram? this area is just one. Okay. Cosine square plus sine square theta plus 0 square equals to 1. Okay, you take the vectors dot with itself and then take square root. Right, this is the length. Okay, so all together, so we have to put in our d theta dz. So theta is going from 0 to 2 pi. Z is going from 0 to 1 plus cos theta. Z times 1. Okay, so what do you get here? Let me see. So we shouldn't do like this. Should we do like this? Yeah, we can. So what we integrate to is 2 pi and then 0 to 1 plus cos. Oh, okay, we cannot do this because dz is depend on theta. Okay, so we have to swap. Otherwise, we need to change our domain. Okay, so the dependent one should be integrate first, okay, and then do the fixed one. Okay, so the first integration, okay, we should get, what should we get? We should get z squared over 2, okay, integrate from 0 to 1 plus cos theta, d theta. So this is just what? I'll quickly complete this. So this is just 1 plus cos theta squared over 2 d theta. Okay, and then you go expand it. Okay, if you expand it and then using a double angle formula, you get half plus cos theta plus 1 plus cos 2 theta over 4 okay, d theta. Then you can just integrate in the normal sense. And all together here, you get pi plus pi over 2 okay, equals to 3 pi. Okay. Okay. Yeah, so this is just the first part. Okay. So we still need to do the parametrization for S2 and S3. Any question on this part or not? Any question? Oh, okay. So the real new technique you learn here should be just parameterize the surface. Okay, how to get the Jacobian. Okay, after you getting these two, then we will return to the chapter multiple integral. Okay, we need to do the normal double integration. Okay, so we are like combining everything we do now in this chapter. Okay, so next, what is x2? Okay, x2 is just a disk. Okay, it's just a disk. Okay, so how do you parameterize a disk? What does this make up by? This is also made up by infinitely many circles, but these circles are decreasing in radius. Okay? Cylinder, you have fixed radius, and then you stack it up. For the disk, you decrease the radius of the circle. Okay, so how do you parameterize your surface? What are the two variables you need? You have infinitely many circle radius in radius. R and theta. Okay, so you need something to control your radius, something to control your angle. Okay, so your x should be just rho cos theta and rho sine theta. Okay, and this where does it lie on? It is lying on the z equal to 0 plane. Okay, so z is always 0. I don't have picture here, but you can refer to the picture back, okay, in the question. So where does this rho and theta lies? Okay, what kind of radius I take? This is a unique disk. Okay, so in particular, the radius is bounded below by 0 and bounded above by 1. Okay, the most you can get is radius 1. And the angle is, you take the full angle, full rotation, 2 pi, full rotation of 2 pi. Okay, so similarly here, we also need to get the Jacobian. Okay, the Jacobian. What's the area of the parallelogram? So if you differentiate with respect to rho, what you get is cos theta, sine theta, and 0. Okay. If you differentiate with respect to theta, you get minus rho sine theta minus rho cos theta. Okay. Yeah, so what's this? I suppose you only get one coordinate, right? Okay. The coordinate you will get is just k. Okay, so it's minus rho cos square theta minus rho sine square theta k. Okay. Only the k minus survive. Okay. Equals to minus rho. Does it make sense? Question? Plus. What do you mean? Oh, plus. Now, let me see. If it is plus, then maybe become a bit weird. Did I integrate something wrong or not? Yeah, I differentiate something wrong. Okay. So I differentiate cos, I got minus sine. I differentiate sine, yeah. Okay. So in this case here, I get rho cos theta square plus rho sine square theta. And then all together I get rho. Yeah, correct. Okay, good. Yeah. Okay, good. Yeah. Okay. So what's the length of this vector here, or the area of the parallelogram in our integration? This is just the rho. That is just rho. Rho times rho and then square root rho square. Okay. Yeah. Okay. Can follow? So I mean, okay, to be precise, this is just 0, 0, rho dot 0, 0, rho, and then take square root. Okay. Yeah. So we do the same usual business. Okay. We do the surface integral. Okay. In fact, there's some quick calculation here can be done. So what is our function to integrate here? It's just z dx. Okay. But on our surface, what is z? 0. Okay. Which means you are integrating over a 0 function. Okay. So no matter what surface you integrate, you will just get 0. So if you can see this earlier, then you don't need to check so many things for your surface already. Okay. So you can skip all the steps. But I'm just trying to show you, if you're going to find the parameterization, how you're going to do it, okay, in future. But if you know that the integral on this surface is 0, then you don't need to find all the Jacobian. Okay, because you are not using them. Okay, last one, S3. Okay, S3. So what is S3? So S3 is Z equals to 1 plus X. Okay, 1 plus X. So Z equals to Fx have a easy parameterization. Okay, for Z equals to Fx, how do you parameterize your surface? I think for function that's equals to Z equals to Fx, how do you parameterize your surface? Overslap. Is it that one? Drink me. Drink of me. Okay, I see. How do you find the parameterized surface for Z equals to Fx? Idea? Sorry? Polar coordinate? Why? Do you always get a polar shape for arbitrary function? So for Z equals to some function in X and Y, the natural thing is just use X and Y. Okay, the natural thing is just use X and Y. Why? Because X only Z. This is suggesting that Z is depending on XY. Okay, and XY are independent, so you could just use XY, and then Z is dependent on XY. So Fxy. So all the vector equation here only depend on XY. Okay, which is what you want, two variables. Okay, so applying to our case here, what is X? What is the X coordinate, to be precise? It's just X. How about Y? Y. How about Z? 1 plus X. Okay. Yeah. So this is the um, form for Z equals to Fxy. Okay, vector function. But in our case here, do we want the whole plane or not? In other words, where do we take our X and Y from? Hmm? Where does my XY lies in? Okay, they live in a disk. Okay, they live in a disk, which satisfy x squared plus y squared is less than equals to 1. Okay, so this is where our xy live in. Okay. So this, remember this here has some convenient way to write down, right? There's one convenient way to write down this polar rectangle. Okay, this is a polar rectangle. So what's the another way to write down this? Testing you to change variable, change coordinate, I mean. R and theta. Okay, you can use R and theta to describe it. Okay. So R is going from 0 to 1, and then theta is going from 0 to 2 pi. Okay, why do I call it a polar rectangle here? Okay, because you can see that I can use 4 scalar number to control this region. That's polar, a rectangle in polar coordinate. Remember, to describe a rectangle, you need to tell me where x bounded by two number, y bounded by two number, right? Okay, but here, instead of xy, it is radius and angle bounded by two numbers. Both of them are bounded by two. Okay, so I call it a polar rectangle. Okay, yeah, so what is the Jacobian here? Okay, yeah, so you can choose to compute it in theta or polar coordinate or xy coordinate. So I choose to compute it in xy coordinate first, since we already have it. Okay, we just need to apply transformation later. So what is the cross product here? Okay, let's compute the cross product sheet first. Okay, so what's this cross product here? It is between 101 and 010. Okay, if you cross these two together, you just get 101. Okay, let's check check the calculation. If you take the length of this is just square root. Okay, so let's try and compute the sorry. You mean there's a -1? Where should be a -1? First coordinate? First coordinate should be a -1. Yeah, I think so. Okay, so if you do the minor here, so you get 0 times 0 minus -1 times 1. Okay, so you should get a -1. Okay. So the sign inside your vector won't change your the length because you are taking square in each coordinate. Okay? Yeah, good. Okay, good. Okay, good. So next, let dx. Okay. So how to compute this? So we need to do surface integral on z. Z in our case is 1 plus x. Okay. And then our Jacobian is square root 2 dA. Okay. So you can see that in xy coordinate here, um, in xy coordinate here, we have this. Okay, you want to integrate over this of xy coordinate. Okay, so what can you do? Huh? Change to polar. Okay, we can change to polar. Right. So we can change to polar. So if we change to polar, what thing we need to introduce? Another Jacobian. Okay, we need to introduce another Jacobian here. Yeah, let us write down first and then I'll tell you more about it. So in polar coordinate is what? X equals to r cos theta, y equals to r sine theta. Okay, so we change our function to polar coordinate. Okay, and then to go from dx dy, okay, maybe let me write down the dx dy, and then you will see why we want to add a Jacobian. So actually, the first dA is on x and y. So now we want to turn it to polar, which is r times dr d theta. Okay. Okay. So r here is what? R here is from 0 to 1. Theta here is from 0 to 2 pi. Okay. So you see here, we have introduced twice the polar. As polar. Twice the Jacobian factor. You know why? You know why? Why we introduced twice? The first Jacobian is for who? Sorry? Parametric surface. Okay. So in other words, so the first one, okay, so we first go from the Jacobian factor for curved surface. Okay. Remember, what's the purpose of surface integral? What's the purpose of surface integral? Because we are no longer integrate on the plane. We are integrate over any surface, any curved surface. Okay. Since this surface is curved, we need to flatten it first. Okay. Once you flatten it, you will introduce a Jacobian factor. Okay. So the next one, why we have a Jacobian factor? That one is just that's just counting the change of coordinate. Okay, you change from xy coordinate to polar coordinate. That's a Jacobian factor. Okay, this is what we learned in multiple integral chapter. Okay, so this one is a curved surface to flat domain. Okay, the second one is a Jacobian factor for change of variables or transformation. Okay, let's say transformation. Transformation of variable. Okay, one-to-one transformation of variables on xy plane. Okay, remember last time when we change from xy to polar coordinate, we have Jacobian factor. When we turn from R3 to spherical to cylindrical, we also have Jacobian factor. Okay, so this is the second one is the Jacobian factor we encountered before. The first one is introduced in this chapter because we are integrate over arbitrary surfaces. Okay, it's curved. So we need to make it flat first. So both of these are the area of parallelogram. Okay, of some parallelogram. Okay. Or not? Okay. So I mean the most confusing things here I think is this. So how many Jacobian you need? Okay, so you need to know what you are doing. Okay. So first the surface integral will give you a Jacobian factor. Okay. Second, if you change your coordinate to other coordinate transformation of coordinate variables, then you need to introduce another Jacobian. Okay, make sense or not? Sense. Okay, we will see maybe more examples later. You will see this keep popping up. All right, so we can see that what are we integrate here? So we can really split the integral. Right? So we just compute the integral. So we have square root 2 of 0 to 2 pi. We can integrate over r first. Okay, we get r squared over 2 plus r cubed over 3 cos theta for r from 0 to 1 d theta. Okay, and then this will just give us half plus cos theta over 3. Okay, and then there's no weird integral here, so we can just do it. Integrating cos theta, we just got sin theta, and then integrating a constant, we get a theta. So all together, we will get square root 2 pi. Okay. Following? Following? Okay. All right. So we have computed the tree contribution from the tree surface here. So the total contribution of the surface is just adding up the tree number. So 3 pi over 2 plus 0 plus square root 2 over pi, which is just 3 over 2 plus square root 2 pi. Okay. All right. Yeah. So continue. Yeah, let's continue. So next, we want to compute no longer surface integral of a scalar field. We want to define surface integral for vector field. Okay, line integral for vector field is called a Wood line, but surface integral for vector field is called a flux. Okay, you can think of a magnet. Okay, how does two magnets stick together? Okay, you can think of some field growing up from the magnet, right? So you got a piece of magnet. Okay, so if you put the magnet here, the magnet will get attracted here. If you put around this magnet, you put any magnetic like metal material, you will get attracted. So they think of this as a field, okay, going around the magnet. So we're going to calculate this. We call it a magnetic flux. Okay. So before doing that, we need to define a direction for surface. We have direction for line, right? So how do we give direction on surface? Normal vector. Okay, so over a surface, you should have normal vector. So we can use normal vector to define the direction. So how many direction you can pick on one point? How many kind of that? How many directions you can pick on normal vector? Two. Okay, either plus, either minus. Okay. Last time we say that normal vector for a plane you can take any direction, right? Because they describe the same plane. But now we consider the direction now. Okay, we call it an orientation. Yeah, we call it orientation. Yeah. So mathematics is like this one. We have an object. Okay, maybe both works, and then next time we do it more precise. We split these two cases. See, these two cases will give different things or not. Okay. In our case, it will give different things. Okay, if we consider different direction. But there's some surface that's not orientable. So what does it mean by orientable? So a surface is orientable if you can continuously give the orientation to the surface. Okay. If you can continuously give the orientation to the surface. So there's some non-orientable surface called the Mobius strip. Okay. Have you seen Mobius strip before? You see Mobius strip before? Okay. So let me show you the Mobius strip. I think I should stop sharing first. Okay. And someone help me to grab this mic. Help me grab the mic. Okay. So let me show you something. Okay, there's a magic. Okay, wait. Let me full screen myself first. Full screen. Yeah, okay. Okay, so how to make a Mobius strip? Okay, how to make a Mobius strip? So you start with a rectangle or a square, okay? So you identify two sides. How do you identify two sides? Here, okay? So if you identify like this, okay, you just get a cylinder. Okay, so to get a Mobius strip, you just need to swap at one end and then you combine. Okay, so this is a Mobius strip. So note that, you see, I put a knot here. Later, I will use this point to start. So there's a point at the back and at the front. Okay, these are the same point. Okay, later you should observe this point. And then I draw a line. For the front part, I draw a red line. The back part, I draw a green line. Okay, so meaning if I finish once full circle here, okay, if I go to the back side, I should get green. Okay, let's see what happened later. So let's combine, let's swap the end and then I combine them together. Okay, so I got this Mobius strip here. Okay, I got this Mobius strip. And let's see why I say this is not orientable. Okay, let's see why I said this is not orientable. So let's start with the point we make a mark. Okay, so let's start with this. Okay, let's say I give one orientation to it. Okay, either up, either down. I give up first. Okay, so what I'm going to show you is if I come back to this point, this orientation will change. Okay, if it changed, then it is not orientable because I cannot give the orientation in a continuous way. Okay, so let's move along the circle. Okay, let's move along the circle. So can everyone see? Wait, everyone see this point? Okay. So I move around the circle. Okay. So let's walk. So I walk. Okay, I walk along this path here. Okay. Wait, let me see. Okay, I walk along this path. Okay, you see? After this green part already end. Actually, I finished one side already. I'm going to the other side. Okay, I continue with the other side, red. And then I come back here. See? But my green point is here. So we are pointing inward now. Just now we are pointing outward. Okay, so there's no continuous way to give orientation. So this surface is not orientable. And why? This surface is actually only have one side. It's only one-sided. Okay. So I combine the front part and the back part to become one side. Okay, one-sided. Okay, thank you. Okay, can get it. I can pass this Mobius band down. You can play around and then pass to your friend. Yeah, if you want, you can play around with it. Don't destroy it. Okay. Okay. So we need to rule out these non-orientable function, okay, to do the computation. Okay, so now on we only consider orientable surface. Okay, only two-sided. Either everything go up, everything go in. Okay, go in or go up. So these are two possible orientation. Okay, either you go up, okay, either you go in. So one thing very visualizing is you can think about durian. Okay, durian. You can think of the what's that? What do you call that in durian? Spine, spine, spike. Yeah, the spike. Okay, the spike is going up. Okay, upward. So it's the outward orientation. Okay, you can think of that. Okay, you can think of the spike as the outward orientation. Okay, it's going up. Okay, so we have gone through this. So we have the unit vector, normal vector. Okay, divide by the length, we get the unique normal vector. But this formula here can be reduced to reduce further to the following for the surface of z equals to fxy. Okay, if you don't want to go through all the cross product, then you can use this formula here. But I'll suggest you to learn the general method. Okay, because it's applicable to all the surface. For the second formula here is just only work for z equals to fxy. Okay, in particular for the plane. Okay, normal vector for the plane, you can use this to find it. So if it is in z equals to fxy form, it is easy to decide what is the outward orientation and downward orientation. Okay, if it is outward, that means your normal vector here must have a positive k component. Okay, must have a positive k component. Okay. So the opposite orientation has unique normal of -n. Okay. Yeah. So I mean, if you can't see what I say here, right? If you can't see what I say here, I suggest you to start with a sphere. Okay. You go and do an exercise. Okay. Start with a sphere. Start with a sphere. Okay. So sphere has positive and negative or hemisphere. Okay. How to describe positive hemisphere? Z equals to square root 1 minus x squared minus y squared. Okay. And the negative hemisphere is z equals to minus square root 1 minus x squared minus y squared. Okay. And then I suggest you to use the general formula. Okay. Use the general formula, compute what is the normal vector to both of these surfaces. And then you should see that the normal vector you compute for positive hemisphere should move up, okay, move outward. Bottom one should move outward as well, okay, although go to the bottom, but it is outward. It's always outward, okay. Please do an exercise. Okay, I want you to do exercise here. So do exercise. Find normal vector. So exercise is find normal vector to positive and negative hemisphere. Okay, using the general normal vector function, normal vector formula. Okay, using the general. Okay, and then see that, and then check whether this comment is right or not. Okay, check this comment here. Okay, check this comment here. See it is outward or not, the normal vector you computed. Okay. And then compare with this formula here. Is it the same? Okay, right. Yeah. So because you are max degree, right? So you should really do this. Try and see. Okay, what is going on here? Any check what? Yeah, exercise. Check find the normal vector to the positive hemisphere, negative hemisphere. Okay. And then compare with the formula here. You have two formula to get normal vector. Okay, compare with the formula here. And then see this comment. Appreciate this comment. Okay, I know I guess you can't imagine what I say here. Right? Since K is positive, this give an outward orientation. Okay, so I invite you to do computation. Check this. Okay, see the K component is positive, and then it is really outward for positive and negative hemisphere. Okay, yeah. So this is always when you read mathematical literature. Okay, if you don't understand the sentence, you really need to put in a example and then do computation and then see it. So you learn discrete math, right? If you shown it, the proposition is either true or false. Okay, either you can see that this statement is true, or either you see that this statement is false. If you tell me I don't know how to do, okay, that means what? That just means that your definition is not strong enough. Okay, you need to go back to the definition, check definition, and then do the work. Okay, if you don't understand the definition, go back and understand the definition first. Okay, and then do the calculation. Okay, don't just stare at it and then think, I don't know how to do, I don't know how to do, I don't know how to do. Okay, when you have a moment that you think you don't know how to do, please go back and read your definitions. So definition is very important. Okay, definitions. Okay, so definition is very important in mathematics. Everything starts from definition. All right, so in the line integral, we need to integrate over closed loop. Okay, now we integrate over closed surface. Okay, over closed surface. So we will say that a closed surface has positive orientation if all the normal vector is pointing upward. Okay, it's like a theorem. If it is inward pointing, then it will give a negative orientation. Okay, inward we call negative, outward we call positive. Is that okay? So you should think of a theorem as a positive. Okay, if a spike go inside, it becomes negative. Negative orientation, positive orientation. Okay. Definition only. Okay. Convention only. Okay, this is our convention. Convention. Okay, surface. Now we introduce surface integral here. Okay, what is surface integral? So surface integral of what? Okay, you need to differentiate surface integral of what. Okay, so now we defining surface integrals for vector field. Okay, if you want to integrate a vector field, dot with a surface. Okay, because both of these are vector function. Okay, you got vector function for your vector field. Okay, you also got vector function on your parametrized surface. Okay, parametrized surface. So you also have a vector function here. So when you dot them together, you take integration. What do you mean by that? Yeah, so this is the definition. So the definition is, you need to dot your vector function with a normal vector. Okay, with a normal vector. So what's this normal vector here? So this normal vector here, I recall the definition we have just now, is dotting with the normal vector to our tangent plane. Okay, divide by the length. Okay, divide by the length. We need the unique tangent. Okay. So you can see that there's some subtlety here. You see a subtlety? This x is both. This x is not both. Okay, both x mean what? It's a vector. Okay. So how I get rid of the vector? I take out the direction. Okay, I take out the direction. Okay, I take out the direction. Okay, so the direction I take out here is the normal vector to the tangent plane. Okay, normal vector to the tangent plane. So this is the definition. So we call this a flux. Okay, we call this a flux. Flux integral sometimes. Okay. So the theorem here is, if you want to compute a flux integral, actually you just need to dot with the normal vector. Okay, you don't need to divide by the length. Why? Why? Why is it true? Why can I throw away the length? Or why does the length disappear? Or why the length get cancelled? Sorry. Then, so why there's no length here? Cancel with who? Cancel with the length. So how do you introduce the length back to my integral? How to introduce the length back to my integral? You see here is x, here is a. What's the difference between x and a just now? Sorry? Just now I briefly mentioned it in the example we did just now. Yeah, why need the Jacobian? S is a arbitrary surface. It's a curved surface. Okay. We want to move it back to xy plane. Okay. Then move it back to A. Okay. When we move the curved surface to a flat surface, we need to introduce a Jacobian. Okay. So what is D here? What is D here? Remember, this D is the domain that define our surface. Okay. This D here is the domain that define our surface. Okay. Okay, like I recall you the example here. So we have this surface here. Okay, we have this surface, this the plane. Okay, what's the domain that define my plane? Okay, so this is the example here. So we got surface. Okay, we got a surface. Okay, defining a plane. Okay, where does my xy lie? This xy are in my domain. Okay, this domain is a flat domain. Okay, I have a flat domain and I put it on a curved surface. Okay, I start a flat domain and I put it on a curved surface, and then I do integration. Okay, so the integration over the curved surface, I need to move all the way back to the flat surface. Okay, so if I move back to the flat surface, I will introduce a Jacobian. Okay, that Jacobian is the area of the parallelogram. The area of a parallelogram is what? Is the length of the cross product of two tangent vector. Okay. So in this case here, what are we doing? So let me go from here to here. So what is this theorem? How to prove this theorem? So we actually move our surface integral back to D. Okay, the D that define my surface. Yeah. So this is the part I screw up in AIT last time. I stuck here last time. Okay, so here is a dA. Okay, so they cancel out. Okay, so what you really need is just vector field dot with your normal vector of your surface. Okay, so you see, like this is really similar to your line integral already. Line integral, you dot your vector field with what? With your tangent vector. Okay. In surface integral, you take your vector field dot with your normal vector. Normal vector of what? Normal vector of the tangent plane. Yeah, makes sense. Okay. Yeah, so this is the upgrade version of line integral. Stood up version. Okay. Any question before I take a break? Let's take a break here and then we will introduce theorem and do example at the same time. Any question before I take a break? No. Okay, let's break for 5 minutes. Okay, let's come back at 12:10. Meter here or no meter? Not here. Later. Okay. 上颚 here. 清风 not here. Basic. 雪岩 江城 嘉业 How you know? Oh. So it's a screenshot and then send. 离开哦离开见玉为烟波藤叶 So 你 Where's 藤叶 You don't know? Fall asleep. 哦临津广结玉京禹州 OK 定柳情真诚 here OK So 你李景见莹莹 not here 莹莹 but balik kampung again So nice Grace 大业嘉文明秀 Michelle Ryan Ellie 雪梅 not here You know where is don't know Okay
能 positive hemisphere 丢去polar 的
诶，不能破啦，这样就算不一样的东西出来了。从破啦再回去，应该可以吧？一样啦，其实
因为我想看
一样啦，一样啦，一样。Actually 一样，只是你 describe point 不一样嘛。诶，OK，
我 expression 真的对上
嘿，I mean，
positive hemisphere 的话是 radius 肯定是零到一啊，没有是我的大约个
不是前，它是没有吗？你的 upper 上面下面是 control by radius，这个还是0到2啊？你还是要一圈嘛？你还是要一圈，你不是上 radius 是0到1吗？0到哪个 degree 是在下面？可是你也不用到0到哪个 degree，这个是 sphere 来哦。sphere 的话，radius 一定是1，
这样我
所以你的 r 是 fixed 的了。
哦哦哦啊，一类是对对，说到最后
这样，
刚上课还没到
等一下他没有问啊。
那个就是你 parameter 然后再给你去用，所以你这边可以达到 x 等于 x 2加 y 2，可以丢进去，那就从这个 parameter 出来。
等你是不是有点 confused 啊？这有点 confused 是什么东西？你不是单在做 algebra 吗？你你怎么不要直接做 RXRY？因为你
所以没有，因为我很多去尾哈，
你给我想一下，你给我想一下。OK，这样你对了，这样你对了，因为你的意思是说你要拿整个 disk，然后你这个是下面的 position，然后这个是上面的 position，这样你是对的，这个是你是对的，
然后我就写哦，然后你就拿到它的
对啊，这样对啊，
然后你就自己直接，因为你讲嘛就是一啊嘛这边，所以这 positive positive，然后这个是 positive，所以可以是 positive，
嗯哼，
positive hemisphere 是 positive，
嗯哼，
然后当讲
哪个地的时候
就
对，
等于负一嘛，
嗯
这不用看了，我们只看 table，我还
嗯
是
嗯。
orientation，
但是你看 negative，它有一个多余的 negative 出来哦，所以那个 negative 被 cancel with 你的那个 negative，所以它就变 positive 了，所以它还是 positive。没有吗？那句话是说 k 是 positive，它才是 outward 吗？不管你在哪里嘛。
哦，
耶，这个你写下来，你 send 给我。
我还
呀，
要改这边，
你就不用改了，不用改了，这是对的。你 OK，你就是
我是
OK OK，
hemisphere，
呀呀呀，
我的
I
hemisphere
mean
我
I
不
mean
懂对不对？
I mean 不用紧，重点是这个东西算出来，所以这一个 for positive 是这个，for negative 是 negative of 这个嘛，对不对？And then 你 I assume 啦，你算出来这边应该是减 r 了
有个负 R 对，
，and then 你就说如果它是0到1，它就是用 positive
对，
用这个，然后0到 negative 1
用下面的。
你就用减 r，可是减就变 positive，所以它一定是永远是 positive。
对，其实我这边做呢，只是因为我不想要为它对 x y，所以我
Yeah，
只是把它变成这样啊。
OK，Yeah，yeah，对，看一下页你要看什么？呀
Flux 到底代表是什么
啊，
？Flux 到底代表是什么？
做 physics，
不知道，
数学就是这个 definition 嘛。
我记得
啊，
中文翻译出来叫通量。
通量，
我在飞机上不是要有一个手飞先，然后你要发出去，然后读出来，要通过一个手飞先才能发。好像那个做题目写的多少，他有先通过一个，就是在面试，不了。
嗯， 等下再讨论 divergence，你再想一下什么是老师，然后你再来问。我也不是很懂，不是 physics
问这个
什么
结构变它本质到底是
？Jacobian 本质是那个 area，因为它本来是 curve 的嘛，curve 那你不能够算它的。Actually，我们的 note 好像有 derivation，只是我没有 go through 吧。如果你看那个 derivation 的话，它就是说把那个弯的线，就是你越看就是 linearize 它了。简单来说就是 linearize 它。你 linearize 过后的那个 rectangle，就是它那个方弯的那个。
所以它也可以贡献在那个 change of coordinate，
对，
同时在这个
对，同时在对，因为 OK，yeah，对，一个是 curve in 3D，一个是 curve in 2D，对，3D 也是圆口边，2D 也是圆口边，yeah，一个 curve in 3D，一个 curve in 2D，yeah，OK，等一下我再讲一个，Yeah, okay. Minshu computed the example just now. Maybe wait for his example and then I can show you. But you should try and compute yourself for the exercise I gave just now. Okay. So um, so just now we say that we have two Jacobian introduced, right? Okay. So first Jacobian introduced here is a curved surface in a 3D. Okay, it's a curved surface in 3D. Okay, then we move to a flat domain. Okay, and then the second Jacobian is we have a curved surface in 2D, and then we're moving back to rectangular coordinate. Is it okay? Can you imagine or not? Okay, so the first Jacobian here is curved surface in 3D. Okay, in 3D. Remember, we have a plane. Okay, when I talk about this, right, you should have an example. So we have a plane. Okay, plane in 3D. Okay, we make it flat to D. D is on 2D. Okay, in 2D. And then how to compute things in 2D, and then we can make it into XY again. Okay. Yeah. So this is the idea. So so you need to be understanding to the theory and also know how to do the computation. Okay, don't just compute. That's why I like to give you concept question in your um, assignment. Okay, because you need to know concept. Okay, you need to know how to compute. Okay, so I rarely give computational question. Okay, because you know how to compute doesn't mean you know what is going on. Okay, or you doesn't mean you know how to explain. Okay? You just do the computation, right? So remember what I said. Mathematics is not just arithmetic. Okay, so you need to do mathematics, right? Okay, so just now theorem can be simplified to the second version here, if you like. Okay, this is a similar derivation as how we derive the normal vector just now, right? So this is the del z over del x minus of del z over del x minus del z over del y and 1, right? This is matching up the normal vector here. Okay, so if you try and use this, okay, use this z equals to fxy, how to get the parameterized function? So z equals to fxy, how to get the parameterized surface? Karen. Okay, xy and fxy, right? Okay, so you have this parameterized surface here, okay, and then use the general formula. Work it out, you should get this. Okay, work it out, you should get this form. Okay, so keep going first. So how about should we do this? What time is it? Okay, let's skip this. Okay, skip this. Okay. Let's continue with stock theorem first. So we want to reformulate our stock theorem. Okay. Last time we said, why are this PQ? I swap the derivative with respect to different variable. Why do we swap it? And then why do we take minus? Okay. Actually, it's coming from the cross product. Okay. Actually coming from the cross product. So we will reformulate our Green's theorem in the Stokes theorem. So let S be an oriented surface, okay, with a continuous varying unique normal n. Assume that the boundary is oriented consistently with n. Okay. What does it mean is, remember we have a curve last time, so it's the same setup. Okay. We have a curve that orient anti-clockwise or counterclockwise. Okay. What do I mean by consistently with n? So on the curve, right? Okay. On the tangent vector here, right? Tangent vector to the tangent to the curve, you can draw a normal vector. Does it make sense or not? Okay, makes sense, right? Okay, so on the curve, you have tangent vector. Okay, over a tangent vector, you can find a 90-degree vector, which we call a normal vector. Okay, so this is a normal vector. Okay, maybe I use a different color. Okay, I mean, we already in different colors, so let's use this. So we use this one. Use this one. Okay, so normal vector to the tangent vector of the curve C. Okay, normal vector to the tangent vector of the curve C. Okay, so use these two, right? You can use the right-hand grid rule to build your orientation. Okay, you will build your orientation. Okay, you can build your orientation. So if you use the right-hand grid rule, okay, there's a normal vector pointing up. Right, okay, yeah. So this is what it means by oriented consistently with n. Okay, you use the right-hand grid rule and then find your tangent normal vector of your n. So this means what? This means that if you walk in the positive direction around C with your head pointing in the direction of n, then the surface will be always on your left. Okay. Yeah. Does it make sense or not? Makes sense on this picture at least or not? Okay. So if you work with positive direction around C, okay, and then you look up, okay, because n is pointing up, right? Then the surface is always on your left. Can you see this from the picture? Okay, so if you are a person here, so you're working along the sea, okay, you look up, and then the surface is always on your left. Okay. Yeah, this is a way to see it, but to find it, this is the right-hand grid rule. So right-hand grid rule, you need two vector. One is the tangent vector to the curve, the other is the normal vector to the tangent vector. Okay. Okay. Yeah, this yeah, okay. Okay, next. So what's Stokes theorem here? Okay. So similarly, we start with a closed, simple, positive oriented, piecewise smooth curve. Okay. So this curve will bound a surface. So we assume that the orientation of the surface should be aligned with the positive orientation of the curve. And then we replace the difference of partial derivative with the operation curve. Okay, with the operation curve. So the loop integral of f, okay, or the work done around, okay. So how should you imagine this? So the work done around the curve C, okay, is equals to the surface integral of curl F, okay. But curl F is a vector field, okay. So how to do surface integral? You need to dot with a vector. Okay, what is the vector you need to dot with? It's exactly the normal vector to the tangent plane. Okay, similar to the line integral, you need to dot with the tangent vector of the curve. Okay, so why is it a curve? Why is it a curve here? Why does it define? Why does it describe the rotational property of the vector field? Okay, how do you do work done in a rotational manner? You need to move the particle in a rotational manner, right? Yeah. So this describes how the vector field rotates. Okay. Okay. So let's verify the Stokes theorem again. So this is a Green's theorem in higher dimension. Okay, let's do this. Let's do this. Okay, so we have this vector field with us, yi minus xj plus yzk. Okay, so every point you can find a vector using this vector field. So if x is a paraboloid, okay, described by z equals to x squared plus y squared, okay, and cut by this circle x squared plus y squared equals to 1 and z equals to 1, okay, as its boundary. So we need to compute these two values. Okay, we need to verify whether Stokes theorem is true or not. So these are the two variables we need to compute. So I already drawn for you this paraboloid, and then there's a boundary here. Okay, x squared plus y squared equals to 1. Yeah. So let's compute these two values here. So how do you compute a line integral for a vector field? Okay, what is this? This is just the word done around a closed loop. Okay, so if you want to do line integral, what's the first thing you do? Parameterize. Okay, parameterize the curve. So how to parameterize this curve? What is this curve? This is a circle with radius. Radius. What's the radius of the curve? X squared plus y squared is 1. 1. Okay, so the radius is 1. Okay. So since the radius is 1, so it is cos t sine t in the xy coordinate. What's the height of this curve? Right. 1. Okay. On the z equals to 1 plane, so the height is 1. Right. So what else do we need when we do line integral? We need a tangent vector. Okay. What's the range, by the way? The range is going from 0 to 2 pi. Okay. So the tangent vector is minus sine t cos t and 0. Okay. How do you differentiate a vector function? You need to differentiate component wise. Okay. Differentiate component wise. Okay. So integrate this. So we change everything to t variable. Okay. Variable in t, so that we can use material from calculus 1. Okay. So we have to dot the two product together. Two vectors. So we are dotting sine t minus cos t sine t, okay, with the tangent vector minus sine t cos t 0 dt. Okay. So if I dot this function together, I will just get minus sine square t minus cos square t dt. In other words, I just get minus 2 pi. Okay. Yeah, no. Trigo identity, I get minus 1, and then integrate 0 to 2 pi, I get 2 pi. So minus 2 pi. Okay. Yeah. Okay. So we should expect if we integrate the surface, okay, integrate the surface on the curve f, we should get minus 2 pi as well. Yeah, let's check whether we get minus 2 pi also. So on the other hand, we need to do surface integral here. Okay, so similarly, okay, same method, same procedure. Okay, we need to parameterize our surface. So our surface here is z equals to x squared plus y squared. What is this form? This is also z equals to fxy form. Okay, so the easiest way to parameterize this surface is using xy. Yeah, using xy. So you get x, y, and then x squared plus y squared on the z coordinate. Okay. Where does this xy lies in? Where does this xy lies in? Where does this xy lies in? In a circle? Circle? Not enough. Circle is not enough. Not enough to get the whole surface. We need this. Okay, everything in the middle here. Again, only we'll get everything outside. So we need a disk. So the domain for my xy is the uniqueness. Okay. We need the uniqueness. So how you imagine this? Okay, how you imagine this? Actually, you should think of it as a unique disk, okay, and then map by x squared plus y squared. Okay, so the unit disk get extend upward. Okay, get extend upward. Okay, get extend upward. So you see, this is unit disk, right? Okay, later we want to do integration. Okay, what's the convenient way to integrate over this? Polar. Okay, polar coordinate. So we can prepare our polar coordinate first. First, we are going to integrate the surface later. Okay. Yeah. So what else do we need? We haven't computed what is curl yet. Okay, what is the curl? What is the curl of my vector field? Okay, what's the curl? How does curl define? For vector field is cross product between gradient operator and the vector field. Okay, please don't forget. Please don't forget. Yeah, please don't forget. Okay. Later I say please don't remember. Okay, please don't forget. So you cross the gradient operator with a vector field. Okay, y minus x, y, z. Okay. What do you get? You should get z 0 and minus 2. Okay, you can check whether it's correct. Okay, so after we get this, anything else we need? Let's try and write down the surface integral first. So curl of f on dx. Okay, so just now we already derived. What is this? What is this surface integral here? Okay, you need to integrate over what domain? What kind of domain you need to integrate over? Any idea? No? You need to integrate over the domain that describe your function. Okay, in this case, it's the D. Okay, you need to integrate over function domain that describe your surface. Okay, in this case, the dot product between curl and your surface is what? It's just dotting with the area of the surface. Sorry, dotting with the normal vector of the tangent plane. Okay, which is n. Then dA. Okay, remember this or not? Remember this? Remember how we derive this? Remember how we derive this? Okay, maybe I repeat again the derivation. So the surface integral here by definition is what? You need to make it flat plus, okay, make it flat. Okay, meaning this is by definition dot with the unit tangent vector. Okay, so you make your curved surface flat first. Okay, and then this is still still curve in a 2D sense. So you need to make it flat again. So you need to transfer it. So here is still x, and then I transfer it back to my flat domain in 2D. This one is this multiplied by the Jacobian. Okay, when I move it back to the flat domain 2D. Okay, so first one is by definition. Okay, but this is a curved surface, so I move it back to flat in 2D. Okay, and then they cancel out. And what we're left with is the thing that we discussed just now. Okay. Okay. Yeah. So, what do we have? Okay, curl D, what do we have? Curl F, we have Z, 0, and minus 2. Okay. What is N? Okay, N in our case is what? we haven't really computed n yet, right? So what is our n? Our surface is described by xy. Okay, so how to find n? 0, sorry, 0, 0, 1. So we take Rx cross with Ry, right? Rx cross with Ry. So what is Rx in our case here? Anyone still have the formula? Yeah, here. So what is Rx here? 1, 0, minus 2x. Okay, what is y? 0, Ry, 1, and 2y. Okay, so all together we get minus 2x, minus 2y, and 1. Okay, so we dot this normal to our vector field. dA. Okay, so all together, what do we have? Minus 2x, x squared plus y squared minus 2. Right? Yeah. Yeah. Okay. But just now we turn our domain into polar coordinate, right? Okay, so we can compute the multiple integral in polar coordinate form. Okay, polar coordinate form. So when we do polar coordinate, we are applying the change of variable of x equals to r cos theta and y equals to r sin theta. So when we introduce dr d theta, we need to get the Jacobian factor r. Okay, so we have r dr d theta, and then we integrate over the domain. What's our domain? Yeah, our domains are all are all scalar. So it's a polar rectangle here. So radius from 0 to 1, theta from 0 to 2 pi. Okay, so when you change everything inside into polar form, okay, what do we get? So we get 2r cos theta, okay, and then r squared. Okay, so we multiply our r. Okay, let's just leave it in this form first. Okay, how to do this computation here? So you can see that the first term here has cos theta, right? So if I integrate from 0 to 2 pi, what do you get on cos theta? You get 0. Okay, if you integrate 0 to 2 pi on cos theta, you get 0. So this term actually disappeared. Okay, what we left with is the second term here. So integrate from 0 to 2 pi, 0 to 1 of 2r, minus 2r actually. Okay, so what is this? This is integrating from 0 to 2 pi of r squared. Okay, and then you will get minus 2 pi. Okay, you'll get minus 2. So 0 to 2 pi 1 d theta. Okay, you get minus 2 pi. Okay. Okay. Yeah. So Green's theorems depend which one is faster to do. You can decide you want to do loop integral or you do the surface integral. I think in this case the surface integral is hard. So loop is faster. Okay. Yeah. Sometimes loop is harder. Sometimes surface is easier, or the other way around. Okay. So you can swap between these two using the Stokes theorem. Okay. Okay. Yeah, so we do an example on a surface integral and then we do an example on Stokes theorem already. So there's some question we just leave it and then I will provide solution. Let's see if we want to do this or not. Maybe we also skip this then. Yeah, let's skip this. Okay, next is this divergence theorem. Okay, divergence theorem. So what's divergence theorem? So just now we relate 1D and 2D. Okay, now we relate 2D and 3D. Okay, 2D and 3D. Double integral to triple integral. Okay, how do we relate this? So in 1D, we have closed loop. Okay, now this is a similar thing. In 2D, we want to have a closed surface. Okay, if you have a closed surface, then you will bound a solid. For example, sphere is a closed 2D surface. It bounds a, what's the solid it bounds? Sphere. What's the solid bounds by sphere? Ball. Okay, you get a ball. Okay, you fill in the ball. Okay, ball. Okay, you get a ball. So in your mind, right? Okay. So 1D, okay, just now Stokes theorem. So some simple example you should keep in your mind. So Stokes theorem, okay, Stokes theorem. You have a simple closed loop, okay. Circle, okay, bound a disk, okay, circle bound a disk. So circle bound a disk. In a divergence theorem, you should think of a closed 2D surface, a sphere bound a ball, okay, bound a ball, okay, a sphere bound a ball. So how do we relate these things? So similarly, we have vector field. Okay, we have vector field. Okay, how we play around with this vector field here. So first, we take the surface integral of this vector field. Okay, so if I take the vector surface integral or the flux interval over this closed surface here, this is equal to the triple integral of df dv. Okay, df is a vector function or a scalar function? Df is a vector function or a scalar function? 三个. Sorry? Scalar, right? Okay, because you are dotting two vectors together. Okay, so you get a scalar function here. Okay, so when you do this triple integral here, there's no funny thing popping out. Okay, we don't need to define new triple integral here. Okay, we are not dealing with triple integral of vector field, nothing like that. Okay, just a normal integration of function. Okay, so this is a triple integral of a scalar function. We do this in multiple integral already. Okay, we can swap it to spherical, we can swap it to cylindrical and do it if you like. Which one is convenient? Okay, but why do we call this divergent? Why does this value on the left test the divergence of the function? Okay, why? Let's examine what's the left hand side here. What's this definition of surface integral? What's the definition of surface integral? Why? What's the definition of surface integral? Just maybe. Okay. Check. You check. Yeah, what's this? I recall a lot of time today. Okay. In example, in introducing theorem. Okay. So I must remember today. So what's the surface integral for vector field? I just finished the example just now. You need to dot with what? Yeah, sure. That's the okay. Yeah, okay. So that's the definition. Dot with the unit vector. So we have this dx. Okay. Or another way you remember this is I turn this into a domain. Dot with a just a normal vector is enough. Okay, because the normal vector, the length cancel out with the Jacobian when we do the change of variable. Okay, transformation of variable. Okay, so you see, what's the orientation we pick here? What's the orientation we pick for our surface? Huh? What's the orientation we pick for surface? Positive. Okay, positive. You should think of what fruit? Durian. Durian is going up, spiking out, right? So for this value to be positive, right? The dot product must align with the positive orientation. Okay, correct or not? Dot product costs have to be 0 or 2 pi, so that is positive. So if your vector field align with the orientation, meaning the vector field is spiking out. Okay, so this value here on the right hand side, we call it a diff. If this function can compute the left hand side number, we call the function diff f. Make sense or not? Okay. Okay. Okay, so another way to think of this is if you want to compute, let me see. Let me see. Maybe I don't redraw the picture. Let me show you the picture. Let me show you the picture. Okay, so another thing is if you want to compute the contribution of your vector field on your, let's say this is the box, rectangular box. Okay, what you can do is you can make infinitely small box and then calculate the contribution. Okay, you can see that the thing in the adjacent, right? You see, going in and going out, so they cancel. Okay, the middle stuff all cancel, and then you add out the contribution, and the side is exactly the same as you compute the contribution at the surface. Okay, so you can think of it. This is the picture on the left hand side. On the picture on the right hand side, why is it related to a volume? Okay, because I can split my object here into infinitely many small object inside here. Okay, and then I look at the contribution of the surface also. Okay, but the way I look at the contribution of surface is through diff f. Okay, although I'm not giving you the proof, but this is the concept. Okay, this is the concept. I didn't write down the proof, but this is the concept. Okay, right? You want to compute a volume of a solid, you need to make small rectangle to approximate your volume. Okay, so this is small rectangle to approximate the contribution of your vector field. Okay, can see? Okay, yeah. Okay, let's continue. Okay, let's continue. Let's continue. So let's do an example here. Right. So let's do an example. So let's do one example here. So verify guess theorem or the divergence theorem. This is the other name for divergence theorem. By calculating the contribution of vector field on your surface. Okay, what's the surface here? E is x, y, z. Okay, x and y is controlled by a disk. Okay, z is controlled by 1 minus x squared minus y squared. Okay, this is not quite a sphere, but a weird sphere. Okay, when you square the sphere. Okay, so you get this picture here. And so you get a picture here. Okay, right. So we need to compute these two values here and then see that they actually agree so that we can check the theorem. Okay, check that this agree. So we want to do surface integral of the boundary of E. Okay, how many boundaries here? Two boundaries, right? Okay, so one boundary is at the top. Okay, and then the second boundary is this. Okay, there are two boundaries here. So boundary of E split into two parts, top part and the bottom part. Okay, top part and the bottom part. Okay, so we need to parameterize both of them. So for first one, how we describe this? Okay, this is a function that satisfies 1 minus x squared minus y squared. Okay, so how do we write down the parameterized surface? This is equal to xy and 1 minus x squared minus y squared, because this is a particular function z equals to fxy. Okay, how to give the domain? What's the domain of xy? Where does this xy lies in? Satisfying x squared plus y squared less than equals to 1. Okay, or another word, I think we saw this the third time already. We can move this into a polar coordinate. Okay, later we want to do surface integral, right? Okay, so maybe it will be helpful. Okay, so how about x2? Okay, x2 is what? x2 is a disk. Okay, is a disk. So in particular, this is a disk on a plane. Okay, you can see that this equation here, this parameterized equation here actually give a plane. Okay, if I take all the xy, but if I restrict my xy to a disk, then this is just a disk. Okay, this on the plane. Okay, on the what plane? Z equals to 0. Okay, plane on Z equals 0. Okay, can follow? Can follow or no? Okay. Okay. So let's do, can we start doing the, yeah, let's do it. So let's do surface integral. Or you want to compute the normal vector first? You want to compute normal vector first? Huh? What? You want to do compute normal vector first? Maybe let's compute the normal vector first. Okay, because surface integral will need normal vector. Okay, so for the first surface, what's your normal vector here? Need to take the cross product between Rx and Ry. Okay, so 1, 0 minus 2x, 0, 1 minus 2y. Okay, so what is this normal vector here? I think we also do this before. Huh? Same as before, yeah. What is this? 2x, 2y, and 1. Okay. How about the normal vector for this x2? How about normal vector of x2? xry also. Okay, but you should be able to see it from the picture. 0, 0, 1. Okay, but should we choose 0, 0, 1 or not? 0, yeah, so 0, 0, 1 is pointing outward, which is inward to the solid. But we want positive orientation for closed curve to apply the theorem. So it has to be pointing outward. So if you want to point outward here, you need to choose the negative. Okay, so the normal vector here is 0, 0, minus 1. Okay, 0, 0, minus 1. So it's pointing down. Okay, so now we are ready to compute the surface integral. Okay, by the way, now it's 12:50. So maybe we will extend for half an hour, okay? Until 45 minutes. Yeah. Okay. So let's compute this integral here. So this surface integral here split into x1 and x2. x1 and x2. And let's compute x1 first. And let's do x1 first. Okay. So what's this surface integral here? Okay, this surface integral here is integrate over d, okay, integrate over d of f dot with the normal vector to the tangent plane, okay, and then dA. Yeah. So you should see the similarity between the line integral, okay? See the similarity between the line integral. So the line integral here become a t variable, become a t variable. It become an interval, okay? So next, in this case here, our f is y, x, and 1 minus x squared minus y squared. Okay. On the first surface, the normal vector here is 2x, 2y, and 1. And dA. All right. So we need to take the inner product or the dot product. So the dot product here, we should get 2xy plus 2xy plus 1 minus x squared minus y squared. Okay. But remember that just now, our domain here is a disk. Okay. So integrate over this is better to use polar coordinate. Okay, so we change to xy to polar coordinate here. So if we change to polar coordinate, we get r dr d theta first of all, and then we integrate over 0 to 2 pi, and then 0 to 1, okay, for the this. So we need to swap everything in xy into r and theta form, okay? So if I swap xy sub x equals to r sine cos theta and y equals to r sine theta, what do we get? We get r for 4r squared cos theta sine theta plus 1 minus r squared. Okay, so you expand everything. Okay, you expand everything. And then you simplify. And then you do integration. You should get this expression here. Okay, so and then you will get cos theta sine theta plus half minus 1/4 d theta. Okay. And then equals to 0 from 2 pi to sine 2 theta over 2 plus 1/4 d theta. Okay. And then you integrate this. This is just a normal trigo integration. So you should get all together, you should get minus 1/4 plus pi over 2 minus 1/4, which is pi over. So in the end, you get pi over 2. Okay. Okay, so these are just normal computation. So let's check whether, okay, we haven't finished yet. We still got one surface to go. So it's S2. Okay. On X2, what is going on here? Okay. On X2, we are taking dot product between yx and 1 minus x squared minus y squared. Okay, what is that? So on dot one on x2, this part is what? X2 is the surface where z is 0. Okay. So my function on the k component is just 0. Okay. First, how about my normal vector? My normal vector, just now we decide we have to take the downward vector, which is 0, 0, minus 1. Okay. So the dot product of these two is 0. Okay. So you get 0. No need to do integration because integrate over 0 function. So altogether, the contribution is pi over 2 plus 0. So which is pi over 2. Okay. Yeah. So you see, so we go through so many stuff. So let's see if we can do it easier using diff f. Okay, diff f. So what is diff f? So let us start with the expression first. So let's do triple integration on the solid bound by our surface. So what's the how you describe the solid bound by this surface? What does this x and y have to satisfy? What does x and y have to satisfy in my solid here? Huh? Means here equals what? R equal 1. Okay, equal 1. Sorry. Yeah, less than equal to 1. Okay, equal to 1 only got one circle. Okay, we we not only want a circle, we want everything inside the circle. Okay, less than equal to 1. Okay, but now only have a this. How to fill out the space? How to fill out the space? You need to use z, right? I need the height. So what height you need to take? What's the height you need to take? Now you got this. So what height you need to take? You need to take. Okay. So the outermost layer is z equals to 1 minus x squared minus y squared. So what kind of height you need to take to fill out the solid? What height you need to take to fill out the solid? Z equals bounded below by 0, okay, all the way up to 1. Up cylinder, right? You get a cylinder, but I don't want a cylinder. I want 1 minus x squared minus y squared. Okay, yeah. Okay, we take up to the surface only. Okay, so this is the solid. Okay, so this is a solid. So we still need the function to integrate over. So we need to compute what is diff f. So what's the definition of diff f? Gradient dot product with the vector field. Okay, so dot product is easier to compute than the cross product. So my f is y, x, and z. Okay, so if I dot these two together, what do you get? Zero, wait, 0 plus 0 plus 1. Right, 0 plus 0 plus 1. Okay, it's not a vector 0, 0, 1. Okay, 0 plus 0 plus 1. So you just get 1. Okay, so if you do triple integral on 1, what do you get? What's the value you get here? Volume of your domain. Okay, volume of E. Right. So do you know how to find volume of this solid or not? Is there any standard formula for this object? This is a sphere, not quite a sphere, right? It's not a square root. So we have to do the, we can do the usual integration here. Okay, so we do the usual integration. So want to compute this object here, which coordinate is better to use? E already, right? So you can choose cylinder or spherical. Spherical or cylinder? Cylinder. Cylinder, right? You see, just now we almost make a cylinder already. So this proves that cylinder is close to this object here. Okay, we just cut part of the cylinder out. Okay, we just cut part of the cylinder out, right? So you see, so this is a part of the cylinder. So cylinder coordinate is better to use. So cylinder coordinate has what? So we have dz, dr, d theta. Okay, so our z is going from 0 to 1 minus x squared minus y squared. And then r is what? 0 to 1. Theta is 0 to 2 pi. Okay, if you like, you should re-express this in terms of cylindrical coordinate. Okay, but I think we just now keep writing the changing variable for x, y, that is a this. Okay, so you should do that as well. So in cylindrical coordinate, what's your contribution from Jacobian? Huh? Okay, it's the same. It's the same as polar coordinate. Why? Because you are exactly changing the first two coordinate to the polar coordinate, and then you fix the third one. Okay, that's why it's similar to polar coordinate. You just get r. Okay, so you just get r here. Okay, so you just do the usual integration. Okay, just do the usual integration here. So 1 minus x squared minus y squared here in the r theta coordinate is what? 1 minus r squared. Okay, yeah. So you can integrate it now. Everything is in r, z, and theta. So we can split the theta out, and then we keep the r part. Wait, okay, yeah, we keep the r part. Okay, and then we can do integration like this. Square over. Okay, so what's this value here? 2 pi times 1 over 4, okay, which is pi over 2. Okay, we get the same value, pi over 2, on left and right. Qingrou, maybe you can wait for a while because we have to finish at 1:30 maybe. You can have a seat because I am not finishing. Sorry, yeah. You can take a seat first. Okay. Okay, so this is a divergence. Yeah, divergence. Okay. So for the other example, you can do it yourself or I will provide the solution. Okay. So to prepare for your exam, right? Please understand everything in the lecture notes. Okay, lecture notes very important. And then do review exercise. Review exercise very important. Okay. So should we go over summary for the content or assignment first? Want to discuss assignment first or summary for? Not yet. I haven't finished teaching yet. Content first, huh? Okay, content first. Okay. And so let me use the one I do for AIT one. 重点 huh? I will throw a main point uh, along going through. Okay. Yeah. Okay. So when I go through this topic, right, I want you to imagine a storyline. Okay, imagine a storyline. Imagine the exercise you have done. Okay, what have we gone through? Okay. So final exam topic we start with partial derivative. Okay, we start with partial derivative. So we start with level curve, level surface. Okay, level curve and level surface of what? Of function from R3 to R or R2 to R. Okay, both of them. And then we look at limit locally. What happened? Okay, when we take limit. Okay, if it's equal at that point, is it continuous? Okay, equal to the value of function at that point, is it continuous? And then we look at how does it change in x direction, in y direction, the partial derivative. And then from these two directions, we build a tangent plane. Okay, what does the tangent plane means? Every curve on your surface, the tangent vector to the curve must lie on the tangent plane. Okay, this is the tangent plane we built. And then we can further differentiate, okay, higher partial derivative, okay, or the mixed partial derivative, because you can take different order. But how does this different order of partial derivative compare? Okay, by Claira's theorem. As long as your second order partial derivative, mixed partial derivative is continuous, they are equal. Okay, they are equal if they are continuous. Then we do chain rule. Okay, we do chain rule. Implicit function theorem. Okay, chain rule, implicit function theorem. So this chain rule is a higher dimensional chain rule on two variables. Okay, we can do up to two variables using the trees. Okay. And then there's no reason we stop at differentiating with x direction, y direction. Okay, we can take linear combination of x and y direction, and then we differentiate along that direction. Okay, but what's the formula? The formula is exactly the dot product between gradient and that function. Okay, and that direction. Okay, so the directional derivative is given by the gradient function dot with u. Okay. By the way, this highlight is not for you. This highlight is for AIT student. Okay, their question include this. But yeah, later I'll mention about yours. So what's the maximum rate of change? So what is gradient? Okay, why gradient is important? First of all, it helps you to compute the directional derivative. Second of all, direction of gradient tells you the maximum rate of change. Okay, the direction gives you the maximum rate of change, and then the magnitude gives you the slope. Okay, maximum slope. Okay. So in the direction of gradient, you get the maximum rate of change. How to get the maximum rate of change? You take the magnitude. Okay, take the length. Okay. So gradient is a gradient of f is a vector. Okay, it's a vector. Don't confuse with the first calculus of one variable, because calculus of one variable gradient is the same as slope, and then it's the same as tangent vector. These are all the same. Okay, but in higher dimension, they're split up. They mean different things. Okay, because you not only get number, you also get direction. Okay. And then you look at tangent planes to level surface. Okay, and then maximum, minimum values, absolute, local. Okay, this thing I want to point out in the assignment later. Okay, I use the example to explain more about this part. And then we have extreme value theorem. Okay, how to find extreme value theorem? Extreme value theorem. How to find local maximum, local minimum, using critical point theorem, and also check using second derivative test, okay, and then Lagrange multipliers, and then we finish the partial derivative. So in partial derivative in our class, right, I spend the most time doing this. So I will have proof from this section, okay. So proof from this section you need to study is the one that are in your lecture notes, okay. You have to study everything in my lecture notes, okay, for partial derivative. You need to know the proof, okay, that I present in the class, okay. We get stuck in the class. They are very important, okay. Yep.
So the proof will be modified another.
Mm, cannot ask this detail. I mean, wouldn't be too hard because you cannot bring cheat sheet in. So, yeah. So I would say lecture notes very important. Lecture notes very important. Okay? So please understand the proof in this sheet. Yes. Okay. Yeah. I didn't say that. Okay. Question. Okay. See you. Bye. See you again. Maybe not. Don't know yet. Okay. Huh? I can't remember. Don't know yet. Okay. So, hey, what else? Yeah. So for this chapter also, I give you the quiz of AIT, right? Those will be helpful also. Those questions. Huh? No, I mean I give them your quiz to do. Yeah. Helpful for you, helpful for them. Okay. Yeah. Helpful for you, helpful for them. Okay. So you guys are neighbor, have to help each other. Okay. The exam, I think you guys seek neighbor. I don't know. Okay. Sorry. You ask OAA. Okay. Ask the office people. Okay. Yeah. Question. No, I mean in anything in the lecture notes that we have present. Did I present the proof? I didn't present the proof, right? I just write the statement down for that one. I didn't write the proof yet. So the proof that I present in class is very important. Okay, present in class. Okay, the proof that I presented in class. Okay. Oh, actually, for your part, I have an extra time spending on open and close set, right? So those are tested as well. I already include the definition for you in the exam sheet. Okay, close and open. Okay, close and open. Be prepared. So I put in a little bit of topology flavor into this course actually. Okay. Yeah, I put a bit of topology flavor inside this course. Huh? What? Not vanilla flavor, it's a topology flavor. Okay. Yeah. So okay. Next, multiple integral. Okay, multiple integral kind of short because they are repeating concept. Because we're doing double integral, doing triple integral. Both of them will have Fubini's theorem. Okay, Fubini's theorem tells you that you can change the order of integration. But if you differentiate over different general regions, then you need to draw the diagram out and then figure out what domain you need to integrate over. Okay, so for this chapter, I think I do a quite detailed summary last time when we finished this. Okay, so you need to know how to use the Jacobian, what kind of Jacobian you use when you go to polar coordinates, cylindrical coordinates, and spherical coordinates. Okay. Okay, the hardest part is the change of variables in multiple integral. Yeah, okay. So this is the Jacobian part. And then I skipped the discussion of chapter 13. Okay, that one is just a preliminary for you to do parametrized curve. So we already do it in chapter 16. So we just straight away discuss chapter 16. Yeah. Yes, that's right. That's right. That's right. That's right. That's right. Yes, yes. If you want to skip the exercise, you can straight away do the vector calculus. But if you forget how to parameterize, and then you go back to chapter 13. Yeah, that's the point. Yeah, that's the point. Yeah, yeah. Because we also don't go detail in chapter 13. Okay. So chapter 16. So chapter 16, we start with vector field. Okay, vector field is a function from Rn to Rn. Okay, R3 to R3 or R2 to R2 for our case. And then we study the gradient of a scalar field. Is actually a vector field. Okay, that's the natural source for your vector field. Okay, gradient of a scalar field is a natural force. So if your vector field comes from a scalar field, okay, we call the vector field conservative. Call the field conservative when f equals to gradient of some scalar field. And then what else? Next, we do line integral. Okay, we do line integral. So line integral we doesn't do on x anymore. Our x move in a 3D space. Okay, our x move in a 3D space. So how to integrate over 3D space? You need to start with a p. You need to parameterize your curve. Okay, make it into 1D. Okay, parameterize your curve. So word done. Okay, word done is a line integrals of vector field. Okay, line integrals of vector field. Just now already keep mentioning it. So you parameterize your curve, and then you need to take the dot product between the vector field and the tangent vector of the curve. Okay, and then you integrate. Then 6, we have fundamental theorem for line integral. Okay, if you integrate over a gradient, okay, it is just take the antiderivative, apply on the terminal point minus antiderivative at the starting point. Okay, this is similar to the fundamental theorem of calculus. This is one dimensional higher, right? So in calculus 1, you use f prime, but here we use gradient of f. Okay. Okay, next 7. We introduce this the following equivalence. So what are equivalence? So f is conservative if the line integral is independent of half, and also all the not and also but all the closed path is integrate to 0. Okay, this is when f is conservative. Actually, it's a pity that we don't do assignment on vector calculus, and I don't test much on vector calculus. Yeah, seems like this chapter is kind of fun. A lot of things we can play around with, but maybe a bit too hard to absorb within the short time period. Okay, so what's important in your exam, right, is how to apply divergence theorem, okay, or Green's theorem. Okay, divergence or Green's theorem. You just need to do the review question, okay, understand the review exercises, okay, and example in lecture notes. Okay, still lecture notes. Everything is very important in lecture notes. Okay, and then we finish with Green's theorem, Kerr-Stokes theorem, and divergence theorem. Just now we go through already all these. Okay. We don't have ODE. ODE is in your other class. Okay, we don't have ODE here. Any question? Yeah. Not really. How to say? Um, Jacobian part. Okay, actually Jacobian part include everything already, right? Because all the cylindrical, spherical, polar, they are actually under changing using Jacobian part. That's why you have the extra factor coming up. Yeah. So actually that whole process, okay, in the multi-integral, right, there's really only, I think, two skill units. Okay. One is finding the Jacobian. Second is to determine the domain. I think that's all. Yeah. So this is the whole key part of the multiple integral. Okay. Yeah. Okay. Yeah. How to apply it? Yeah. Yeah. That two theorem also include everything in front already. But yeah, but I mean, if I yeah, right, yeah. Yeah. Unless we can play something with conservative or vector field, but I didn't put. No, I didn't highlight for you. The next one. Highlighted one you must know how to do. No highlighted one you also know how to do. Better no, okay. Otherwise, your knowledge is like one part, cannot connect, Later AI compute wrong, you also don't know. You stupid, later you take the answer. Okay. Right, yeah. I think six or seven. Okay, wait. 6 or 7, but we don't have so many part in one question now. Only one shot. I mean, there's no multiple part in the question like last time. Last time we got like one question got 4 part, 5 part, right? Yeah. So it's now like split already. One question, mostly one question, one part. I still have concept question for you. Okay, still have true false question. Okay, so better no, you don't have. Yeah. And the definition I gave in the formula, if you want to remember, you better remember. Okay, so I give you the formula sheet, right? So those are the formula I give to you. If I don't give to you, but you want to remember, memorize, then please do it. Okay. Have you all seen the formula sheet I post out? Yeah. Okay. So those are provided in the exam last time. Yeah. True, prove it. False, give an counter example. Hard to say. Yeah, hard to say. Okay. Concept. Definitely concept question.
So this one apply question more or
I think apply more. Okay. Apply more, but I think about 40, 60 like that. 40, 60. Something like that, yeah. I mean, I forgot it's 40, 60 or 30, 70. And most go to 30, 70 only. Okay. In my class, I definitely want to test concept. Okay, in my class, I definitely want to test concept. Hey, I think that one is a bit too much already. This is like, this is the data we have to give to the school when we set the question. Okay. Yeah. Any more question on exam? Yeah. Ah, rings or rings or divergence. Stocks, yeah, stocks, stocks and divergence. Yeah, sort of. Yeah. This theorem require you to know how to do Lorentz integral and surface integral. Okay. Okay. Yeah. Any more? Any more? AIT we don't put concept is because other lecturer is very picky of you guys. Because there's other class also. Huh? Yeah. Okay. Okay. Yeah. Any more on exam? What to focus? Okay, so let's move to assignment first. Okay, finish assignment first. Okay, assignment. This time I only put 2 concept questions, right? 3 calculation. Okay. So why I don't want to put too much calculation is not challenging. Also, even when I was marking, also not challenging because all the steps are the same. Okay. So I just number correct, tick. Okay. So when we involve concept, then I will see what are you thinking, how you think. Okay, how you think about the question. Okay. So the first question here, prove that f is differentiable, then f is continuous. Okay, so this is a very standard question in analysis. Okay, so to prove this, actually very easy. Okay, you just use definition. Okay, so the definition, you take the limit, apply limit in 2 variables, then you will get the continuity in 2 variables. Okay, I posted out this solution. You can check. If you have question, you can stop me at on the spot. Second, I prove that I give you 2 definitions of concept. Okay, I prove that they are equivalent. Okay, how to do this? Okay, you need to use logical equivalence. Okay, if and only if. Okay, prove left to right, right to left. There are 2 definitions. First imply the second. Assume the first, prove the second. Assume the second, prove the first. Okay. So for this question, right? Even if you can't imagine closed set, you should be able to do using the definition plus the set theory. That's all you need. Okay, you don't need to even imagine what is closed set. Okay, just plainly using logic, you can do it. Okay, logic plus set theory. Okay, you can prove this question. You don't need to understand what is closed set, but after you do it, of course, you should think about what is closed set because it is very important for your exam. Yeah, very important for exam. So please think of it. What is closed set? What is open set? What is open and closed set? What is not open and closed set? What is closed and not open set? What is not open, not open set? Okay, all this, please think about it. Okay, I will give hint. I don't want to repeat anymore. Okay, please think about it. Okay, very important. Okay. Yeah, very important. All the possibility, please think about it. And please don't ask me, I won't tell you because I will give you hint. So part 3. Find the extreme value here. Okay, someone asked about this question. And who asked me last time? Who messaged me about this question? Anyone of you remember? You asked whether you need to determine whether it's a local extreme. What did you ask? Repeat again your question.
I asked whether because this question is hard to determine the I guess it's local extreme.
Local extreme.
Yeah.
Okay.
Because some case. Well, I think it's the whole.
Okay. Okay, sure. Okay, yeah. Okay, good. Okay, I know what you're talking about. So now you see this question here. I didn't specify absolute. Okay, I didn't specify local. Okay. Let's see why I don't need to mention this word here. So I want to find extreme values of a function. Extreme values mean what? Maximum and minimum, right? Maximum and minimum. On the region bounded by origin 0, 4, and 4, 0. Okay. I think who the one that left. Zheng, yeah. Zheng miss out the origin. Okay. So you need to read properly the question in the exam. Make sure you read properly. So there's the origin 0, 4, and 4, 0. So you make up a triangle, not just a line. So extreme values theorem says if it is closed and bounded, you must achieve your absolute and absolute maximum and absolute minimum. Also, that means you must achieve the highest value, absolute extrema values, okay, inside this region. But does this absolute maxima equal to the absolute maxima outside of? I mean, absolute maxima of the function itself. This function is defined on every xy, right? Okay, so it's defined on every R2. Okay, so is it the maximum you found is maximum for all? No. Okay,
So the extreme value theorem just tells you the absolute maximum and minimum within the closed and bounded set. Okay, it is not for all. Okay, maybe outside this region, this function is increasing. Okay, so that maximum just a local maximum for the function itself. Okay, so you need to see what's this question asking. This question asking within this region or on the big big domain defined the F. Okay. In particular, in this question here, actually you have 3 critical points. Okay, actually you can find 3 critical points. The one critical point is at, okay, so yeah, like what you say, you have critical point on the whole boundary line, okay, 0y and x0, I guess, and then what, and then 2 1, okay, and then 2 1, okay. So also one more point here on the, I think this is on the diagonal line, is it? Is this on the diagonal line? This is on the diagonal line. On the diagonal line, you also get 1 critical point. Okay. But does this critical point happen to be local max or local mean or no? Did all of you found this point here? This extra point here? Do you think this is a local max or local mean? How do you determine it? Okay, one way you do is you can use the neighborhood. Yeah, straight away from the definition. Okay, straight away from the definition, you check. Is it increasing on one side or not? Is it decreasing on the other side or not? Okay. Yeah. So if you do that, actually you can see that this is not a local maximum, not a local minimum, and also not a saddle point. Remember, how do you find this point here? This point is only maximum along a line. Okay, it's not on a plane. Okay, along a line, that is the highest one. How about a plane? Okay, so what should you imagine here? So where's my, okay, so what should you imagine here? So along a line, maybe it is the highest one. Okay, but if I add extra dimension, okay, if I add extra dimension, maybe the shape is something like this. Okay, then it's not a local maximum, local mean, or saddle point. Okay, yeah. So it's only maximum at one direction. How about the other direction? What happened? Here we don't know. Okay, either we take the derivative test or either we take the neighborhood to check. Okay, or yeah, right. Okay. How to check all the neighborhood? How to check all the neighborhood? You need to look at how this function behaves. You need to sub the, okay, so you need to give a description of the neighborhood. For example, this, okay, you put this equation. So you look at the function on this. Okay. So how to see neighborhood, right? So maybe you can also see from direction. Keep a slice. Okay. What's this? Okay. For example, I want to prove that this is not local maximum, right? I only need to find a direction that is increasing. That's all. I don't need to look at the whole, I don't need to look at every direction. I just need to find one direction that violates the local maximum. Yeah. Okay. And then 4, wow, 4, I really admire, I think 2 of you, Qi Feng and Pishon. You guys just plan straight away do this integral. Okay, but I think Pishon got the right answer, but Qi Feng goes somewhere else. Yeah, okay. So I mean, yeah, so you should also learn, okay? I mean, you can do it, but you should also learn how to use a different change of variable to do it, okay? If you see so many square root, square stuff, you should think of a polar, okay? Right, square root of some square, okay? You need to think of polar. Okay, try to draw this. Try and learn this method, okay? Yeah. Yeah, I think you guys use what sec tangent. Did you find somewhere else? Or that one is learned in calculus 1, is it? You use secant. Yeah. Yeah, one whole page. By the way, do you use computer to check answer? Or not? You use, okay. Otherwise, I think we'll get lost easily. Qi Feng, just believe in yourself. Is it? Yeah. Okay, I think Qi Feng, please work harder. I think you have the potential, but you're a bit lazy. Okay. Yeah. Okay. So 5. Yeah, 5. So 5. So in the class, I already proved this using polar coordinate, and then I ask you to do it in triple integral. Okay. So I guess the easiest way is to use cylinder. Okay, a lot of you use cylinder. I start with spherical, so some of you also start with spherical. Yeah, and then means you do both. Yeah, means you do both. Yeah. Okay. Any question on assignment or not? Farah? Yeah. Good question. I didn't check neighborhood here. Yeah.
Differentiate it with respect to to different directions, and I check the
The slope. Just share a check on that point. If this slope, okay, if along this line, okay, if along this line the derivative is not 0, then meaning it is increasing or decreasing already. If you found one line is 0, and that means it is still a stationary point. Right. Yeah. But sometimes it is a saddle point, so you need to be careful. And yeah. Yeah. Okay. Any more question related to lecture notes or exam content? No more? No more. No more. Do you remember I asked you the first question when I started this class? Huh? What's the first question I asked you when I started the class? Why I choose math? Why you choose math, right? You guys already answered, right? But I haven't answered, right? Yeah, right. Yes. Okay. Please answer. Yeah, I'll answer it now. Okay. Yeah, so where should we start? Okay. What? Okay. Why Okay. So I go to your open day. Okay, SMU open day. I get one of the leaflet here. Bachelor of Science Mathematics in Mathematics and Applied Maths. Okay. I put arithmetic here. Okay. So to show you that this is a maths degree, not arithmetic math degree. So you are not here to just apply theorem. Okay. Not counting. Okay. And then see here. Career opportunities. Career opportunities. The first one listed here is what? Mathematics. Okay, but in your self-review, right, you wrote to me. Don't give question like what mathematician solve. I don't know who are you, but please get the right expectation before you come to degree. Okay, we are here to train mathematicians. I don't care whether you become a mathematician or not, but you pay to learn the traits of mathematician. Okay, I don't care whether your job is mathematician or not, but you come to learn the character as a mathematician. Okay, and then you can choose other things. Okay, if you love money, go for it. Okay, not my business. Okay, but Okay, so please get the right expectation, okay, before you come to degree. Okay, so actually your class have kind of quite close connection to me. Why? Okay, first your midterm exam scheduled with my birthday. Okay, but actually we delay our midterm, but in the end it get tested on my birthday. So it's like I'm like give birth, like you are give, I mean you are born, I mean right. So you I mean you also my first next student, right? Okay, and then you first get tested on my birthday. So it's like you are born on that day. And then I think it's two coincident, okay? Coincide with my graduation. My graduation is graduate on 13th of July. When's your final exam? 13th of July. You also 13th of July. Okay, you also my child, okay? So you see, I graduated from my degree, you also graduated from my class. Okay. So I really hope that you learn something from this class. Okay. But so please learn something from this class. If you don't learn it, then I think it will be a waste. Right? It's a waste. So yeah, so that's why I don't really believe probability, you know. So I don't like probability. I seriously don't like probability because I don't like the philosophy of probability. Let me tell you, if you calculated the things that happen 99% degree, okay, if it won't happen, if it won't rain, then it won't rain. Compute whatever you want. But if it won't rain, it won't rain. Okay? I mean, this is my own philosophy. You can choose to follow or not. Okay, so speaking of my graduation, right? Okay, I wrote this. So Wayne asked a question. What's mathematics to you? Okay, what's mathematics to you? So I wrote this poem in my thesis. I wrote in 3 languages. Okay, because I was raised in three languages: Chinese, English, and BM. Okay, Chinese, English, and BM. But actually, all of these are not my first language. Okay, I speak Fuchua at home. I speak dialect. These are not all my first language. Okay, so I was raised in Chinese, English, and Maths, BM. So maybe talk about the English part here. Okay, so in my secondary school, right, my Maths teacher, every time we ask her, what's the exam content cover until? Then she will say, kindergarten until now. From kindergarten up to now, he say. Okay. Yeah. So kindergarten up until what we learn today. Okay. So I wrote my thesis. Okay. The 28 years then I finished this thesis. Right. And then what is maths? Okay. I tell you it's truth. Okay. It's beauty. Truth and beauty. Okay. But truth and beauty, actually, there's one more thing. You need to be kind. Okay. Because maths is a very noble knowledge. Okay. If you're going to use it to do bad thing, it can be real bad. Yeah. So please, if you learn mathematics, please be humble and kind. Okay. Please be humble and kind. And then next part is the topology and algebra. So this is what I did in my thesis. Topology and algebra. Use algebra to describe topology. Okay. And then finally, why where this topic come from? This is coming from gravity physics interpretation. Okay, so why I do maths? Okay, so maybe I also feel disappointed. Okay, maybe a lot of your comment right hit me also. Okay, I feel the same. Okay, I feel the same before. So I actually copy the feeling when I first take the maths exam to you. You know, so I'm taking the exam from my school for you to do in the midterm. Okay, exactly the same setting, cheat sheet, and then exam question. Okay, very hard exam question, concept question. Maybe you don't even understand the question some of. Okay, so that's normal. I want to tell you this is very normal. This is very normal. Okay, maybe you will ask me if it's so hard for you. Okay, you think that you are going to fail. Okay, Of course, I mean, I did very good in my, so our maths have two parts. One is linear algebra, one is, we call analysis, not calculus anymore, analysis, because we deal with epsilon delta stuff already. So analysis part, I think I failed after I finished. This is the first time I feel that I failed in maths. I never failed in maths. Okay, like Pishon said, I think I'm very good. Okay, I always get 190 above. Okay, but do you really know what you are doing? Are you computing or not? Or you just know how to follow the step? It is not to say that follow the step is not good. You need to know how to follow the step, but you need to understand the step at the same time. So this is why you do tertiary education now. Okay, if you don't appreciate this, if you don't do this, then it's a waste. Totally waste. Okay, totally a waste. Yeah. So why do I keep continue? So I still see truth and beauty in math. So that's why I continue. Okay. It's like no way I can find this kind of stuff anymore. So that's why I choose to continue. Okay. I can tell you every semester, every year I struggle. Okay, but the struggle becomes less and less and less. Okay, but you still struggle. Okay. So I think what I got a comment from Kailen or Yingyu. He said that my semester feel like 1 year. Does it feel like 1 year? Okay, right. That's right. Because I put a lot of things inside. Okay, I put a lot of things inside. This is similar to what I do, what I learned last time. They also put a lot of things inside. Okay, but some of them they lack explanation. Okay, but I add my explanation. But sometimes seems like adding explanation is not giving a good feedback. Why? Because you haven't start appreciating that. So you will miss my comment. Only when you start appreciating it, you will know what I've been commenting every time. Okay? Please think about it again. Because similar to me, okay, I also think that this lecturer not good, don't know how to teach. Okay. Sometimes the way they convey is you can't get it. Okay, doesn't mean that he or she is not good. Okay. So if the lecturer still care about you, that means he or she is good. I met a lecturer, okay? I asked for office hour. I go to the office hour, okay? Like Qingrou, you ask me for office hour, right? Like you step in, he step up. He go to other place. Okay, you knock on the door is locked. I think it was a differential geometry course that was really hard. Harder than analysis. You're gonna be analysis next semester, differential geometry is even harder. There's no exam for the differential geometry for us, only assignment. But you have time to do it and then you can search for it, so it's okay. It is hard, but yeah. So yeah, so what I want to say is if your lecturer is still communicable, please communicate with he or she. Maybe he will scold you, but please learn something from him. Okay? His bad stuff, of course, you don't learn. Okay, learn the good stuff. Okay. Yeah. So please learn. Please learn whatever you can. Okay. After this, you go out and work. You can't learn much more already because you have responsibility to hold on to. Okay? Cannot learn freely like this. Okay? One very important advice for your class, specifically for your class. Okay. Because your class is very similar to my first semester class, DMT class. Okay. Some of you don't understand English. I mean, hard to understand. So it is hard to catch my word sometimes or instruction. So you will miss a lot of idea. Okay. I can see it from your submission and so on. Okay. So please listen carefully to what people say. Okay. Please listen carefully to what people say. And then be humble, be kind. Okay. Learn how to communicate. Okay. Yeah, I'm not sure I will be meeting you all or not, but it's yeah. Okay, so I mean, please keep improving yourself, and then I mean, you see, you have a lot of assignment, right? So maybe I know you put a lot of effort already, but sometimes when I see you guys doing stuff right, please be a little bit more efficient. Efficient. Okay. So since you have this practice, you should take it as a practice and then train your efficiency. Okay. It's not always you will meet this kind of circumstances. Yeah. Right. Okay. For example, the first time I come to this school, right, I feel like, why so free one? Because previous few years I keep working under intense environment. Okay. Right. Okay. I doesn't mean free, free means don't use brain. Okay, the word, I mean, yeah, free means don't use brain. Okay, in the word here is a lot, but they don't use brain. You know what I mean? Like the admin word. There's a lot of admin word, but you don't need to use much brain. Okay? You get what I mean? Like key in and then fill in form, those stuff. You have word, but not kind of word that use thinking, apply much thinking. Okay? But not sure. I mean, I want to get a break from research now because I feel a bit tired doing the PhD research. So yeah. So I also slow down my own tempo. And then I meet you guys. Why? Until I found you. Okay. Until I found you. So I spend time on you. Okay. So you are the one that I train. Okay. So I believe you guys. And so in future, if you have chance, okay, even though if you already decided you want to go apply or pure, that's fine. But if you have chance, please do some classical pure maths course, like algebraic geometry, differential geometry, algebraic topology. Okay, please take chances to learn this because you will never learn this after that. And if you learn it good, you like it, okay, please come and find me. Okay, we have a big project connecting every part. Algebraic geometry, differential geometry, and topology.
Itu spoil your big project.
I spoil nothing to spoil lah. I mean it's
You want to hack the national system.
yeah. Yeah. Okay. Yeah. So please learn this classical maths subject. Okay. Because it's very rare in Malaysia to get this subject. Very rare. Even you go to the top uni in Malaysia, I don't think they have it. Even they have it, I don't think they can go how far deep. Okay. Yeah, so I was trained. So why I teach like a pure mathematician because I trained in pure math. Okay, I rarely did apply math. I don't know how to do Python coding. Okay, but you will have a chance to learn it. That's good. Okay, maybe I also need help for math lab. Yeah, I need to do some computation. So I do computation on this big A3 paper, you know. So if I have a computer, then maybe we can do it. Yeah. Correction, project one correction due date is on the 17th. Is it Monday? Yeah, Monday. Okay. I think project two maybe I won't accept correction anymore because I haven't have time finish marking. Earliest is before your exam. If not, then that's it. But I will mark and then I come back to you. Definitely come back to you. But project one, I accept correction. If you correct it, I can give you up to 2 marks extra. Okay. Of course, you don't simply correct it and then give me this core correction. Okay. Sorry. Please talk to me first what to do and then correct it all for once. Okay. There's no going back and forward anymore. Okay. Any more questions before we break? Then truth and beauty. Truly beauty.
How do you see number as beauty?
Beautiful, huh? It's like can verify. You can verify for different method. You can verify it.
After the form of model on Teams.
Put this on Google on Teams. Okay. I mean, this is in my thesis. You can search it on my website. You can find my thesis. For now, I believe string theory. So I put down the string theory. String number. And yeah, so let's take a photo before we leave. So maybe we ask AI, he didn't have anything.
Oh, AI, you open ChatGPT.
No robotic armor. What? So that so then啊，那金宝。一些男生这样子，然后蹲下来，girls no need, some boys, something like that, a line. Seng上面包吗？还是包？包啊。还有啦，好的，1小时3杯大杯的，把举起来了，非常有力的，要把那个。
起来了，六遍。哦，有点。你把对跑抬起来啊！还要多远的人家？算了，不能报。我们讲什么？有，不会，我不会，躺下来。你们的肩膀，然后一个人不大的样子。阿鲁巴啊，阿鲁巴啊，对了。哎，你们啊，你用2个人够了的啊。你要先靠近，等点对不对？呀。哦。加。
Okay, thank you everyone. So good luck in your exam. So you still can contact me, but maybe I'll be a bit slow in reply. So you still can contact me. Okay, thank you for the semester. Yeah.
没有背包买了，背包买上了。要我回去了，我应该要跟胖哥包的。但是有一说一，地平线在我。哇，南风，我写到10点不早写了，去玩这件。走呗，我准备。拜拜。我都不承认。
关掉我的电脑。哎，昨天哈。